All right, everyone. It is 11 a.m. UTC, so we're gonna get started. Our second day. Uh, our first lecture of today is actually a memorial lecture to celebrate the life of Dr. Kirill Kovtunov. Kirill Kovtunov was the leader in the field of parahydrogen-induced polarization. He was a very close friend of mine and a very close collaborator for well over 7 years. Unfortunately, he died from complications of lymphoma cancer in May 2020. And today's memorial lecture will be presented by Professor Igor Koptyug from International Tomography Center in Novosibirsk, with whom I have a huge pleasure of collaborating for many, many years. So without much additional words, I'm going to give the floor to Igor.
Can you hear me?
Yes.
Good. Okay. First of all, I'd like to thank the organizers for putting this meeting together. And okay. And also for inviting me to give this presentation. I have very mixed feelings about this because all these tragic events are very recent. Kirill passed away on May 19th of this year, and never in my worst nightmare could I imagine that I would be talking about his research under the circumstances like this. But there's nothing we can do about this. What we can do is we can celebrate his life and his scientific achievements. So let's do that. Well, the story begins in 1983 when Kirill was born in the city of Barnaul in the Altai region, which is 200 kilometers south of Novosibirsk. Well, he never walked this route. Obviously, he used to drive a lot because his parents lived in Barnaul. Now, let me zoom out to show you where we are with respect to the rest of the world. Moscow is about 3,000 kilometers west of Novosibirsk, so we are far from many things. We are actually much closer to Kazakhstan, to China, and to Mongolia. Now, in the year 2000, Kirill came to Novosibirsk to become a student at the Novosibirsk University for 5 years. And in 2003, he came to the International Tomography Center to do his diploma thesis research. This research was about applying magnetic resonance spectroscopy and imaging to study and compare the flow of liquids and gases in some simple channels, but also in more complex geometries like these fiber bundles, the microreactors, imaging water in the voids of the structure, obtaining flow velocity maps, and also using PFG and MR to show that indeed liquid and gas flow very differently in these structures. Well, then in 2005, he graduated from the university and came to my group as a PhD student, and here you can see him in this photo. At that time, my group was involved in the studies of what we nowadays call operando studies of catalytic processes. We have designed a setup which allowed us to place either a single catalyst pellet or a granular catalyst bed inside the probe of the microimaging instrument and studying the dynamic redistribution of liquid phase, either in a single catalyst pellet or in a granular bed, and also doing spatial resolved NMR spectroscopy, mainly with hydrogenation reactions. Now, these reactions were performed using normal hydrogen, but we certainly knew about the work of Bowers and Weidekamp, who demonstrated that hydrogenation of acrylonitrile to propionitrile with ferrohydrogen in solution using Wilkinson's catalyst, the rhodium complex, provides the enhancement of NMR signals, not only of the products, but also of reaction intermediates like these dihydride complexes here. And we also knew about the research of other scientists involved in this field as well. Some names are shown here. But we also knew about this paper, which stated explicitly that HEP should be impossible in heterogeneous hydrogenation processes. Well, despite that, the main objective of Kirill's PhD thesis was formulated as demonstration of HEP and in heterogeneous hydrogenations. Now, another part of the story was developing concurrently, and this was about grant application to the US Civilian Research and Development Foundation cooperative grants program, which we submitted together with Alex Pines. And the project was about using HEP in catalysis, chemical engineering, and ultra-low field magnetic resonance. We wrote this project together with Song-Yi Han, but by the time the project started, she left Berkeley, so the main participants from the Pines group in this project were Christian Hilty, Scott Bird, and later Sabi Anwar and Louis Bouchard. You can see here Song-Yi, Scott, and Christian in this photo. There was another second joint project in which Louis, Scott, and Thomas Thijs participated, and this was more about exploring the long-lived spin states, but this was later. But in this first joint project, we actually put a very long list of objectives covering, I think, basically everything from flow, filtration of hyperpolarized fluids, mapping, detecting reactants, reaction intermediates, polarization transfer to heteronuclei, remote detection, studying porous materials with squids and ultra-low magnetic resonance. Now, this was certainly very challenging and ambitious, but now looking back, I should say that we have achieved the better part of this over the last 15 years, certainly not during the term of that project. But then this first item, the primary objective, demonstrating HEP with heterogeneous hydrogenations, was actually achieved at that time. After some initial unsuccessful experiments, Kirill and I came to Berkeley in the end of 2006. And this is when the key experiments have been performed. First, with hydrogenation of styrene into ethyl benzene in solution using Wilkinson's catalyst immobilized on silica or on a polymer. And as you can see, the clear Pasadena type effects have been demonstrated. Importantly, when we remove the catalyst, and it's actually very easy to do with these solid materials, there is essentially no effect. So it was promising, but we were not completely satisfied. We wanted to have more definite proof that what we see is indeed heterogeneous HEP and not, for instance, simple leaching of the metal complex into solution and then observation of conventional HEP effects in solution. And that has been achieved as well in the hydrogenation of propylene into propane, which are gases, using, again, either Wilkinson's catalyst or this cationic rhodium complex on silica, demonstrating Pasadena type effects as well as Altadena type effects. So here, since there's no liquid phase, no leaching of catalyst is possible. So this is the ultimate proof that what we see is indeed the heterogeneous field. Now, studies with such immobilized metal complexes continue even now, and we have many other examples. One example is shown here, the experiments done together with our Spanish partner with this cationic gold complex on metal organic framework, hydrogenating propylene to propane, normal hydrogen, parohydrogen, clear HEP pattern. Well, at the same time, these immobilized metal complexes are not very stable quite often. So this is why they are not used in industrial applications. Well, in industry, they mostly used, for instance, supported metal nanoparticles for such reactions. But in this animation prepared at some point by Kirill, it is shown why such catalysts are not supposed to give any HEP effects. And this is because hydrogen can be absorbed dissociatively on the metal. The atoms move around very rapidly. So then when the substrate comes in, it grabs random hydrogen atoms. So it seems that pairwise addition is impossible in such catalysts. But Kirill was not quite convinced. So actually in less than a year, he has demonstrated that using, for instance, supported platinum nanoparticles, hydrogenation of propylene to propane can in fact produce HET-PHIP effects in pasadena and alpha-dena mode. Now, interestingly, the very first successful measurement that he performed was this ugly spectrum obtained for palladium catalyst alumina. Now, as I mentioned, at that time, we were doing a lot of hydrogenation imaging using normal hydrogen, and someone else used this catalyst in these imaging experiments. And to accelerate imaging, this catalyst was actually doped heavily with permagnetic manganese ions, which Kirill didn't know. But then he got lucky, the experiment worked despite that, and then these later results followed. Well, we had to explain why we see these effects on supported metals. And this is the explanation we advanced in that study, saying that, in fact, the metal surface is never clean during the reaction. It is covered with lots and lots of species. And maybe the metal is actually partitioned this way into smaller clean patches so that when the reactants come in, they are forced to stay together. And thus maybe how this pairwise hydrogen addition occurs in these catalysts. However, this explanation has never been proven or disproven so far. Now, based on these innovative and exciting results, Kirill has defended his PhD thesis in 2008 and successfully with flying colors, but the work of course didn't stop there. So ever since, the scope of heterogeneous HET-PHIP has been growing, covering all sorts of new catalysts, different metals, particle sizes, supports, substrates, conditions, and so forth. So to give just some examples, the collaborative work with our Swiss partners using copper nanoparticles. And in this case as well, we can observe pronounced HET-PHIP effects, also showing that if we introduce a phosphine ligand to the metal, the polarization increases, but at the same time, the activity of the catalyst goes down quite a bit. Other systems like these cobalt nanoparticles on titania showing pronounced HET-PHIP effects, despite the fact that the cobalt nanoparticles are super paramagnetic under these conditions. So this observation is quite surprising. Many other catalysts, in addition to metals supported on oxides, we've done work with bulk unsupported metals, metal oxides, as demonstrated here for ceria, for instance, chromia, also metal carbides, like molybdenum carbide showing pronounced HET effects in hydrogenation reactions. Also, sulfide catalysts, like this molybdenum sulfide, which allowed us to study the mechanism of paraffin hydrodesulfurization reaction, which is a model for desulfurization or purification of fuels in industry. And also other important, industrially important processes, their mechanisms and kinetics have been addressed. Now, as we have seen, a lot of work is done with gases, and there the problem is that the lifetime of polarization is quite short. So there's been a lot of effort trying to extend this lifetime, together with our longtime collaborator, Igor and his group. For instance, exploring the properties of long-lived spin states at low magnetic fields, and also dissolving polarized gases in liquid or condensing them into the liquid phase, going to tens of seconds of relaxation time this way, exploring other ways to produce hyperpolarized propane, for instance, by hydrogenating cyclopropane. And this example is interesting because here the main reaction product is actually symmetric. So it's quite surprising that polarization is observed, and some mechanistic explanations are required to explain this. One very recent example, again, collaboration with Chekmenyov's group, is the production of hyperpolarized diethyl ether, which is an inhalable anesthetic by hydrogenating an unsaturated precursor with pyrohydrogen in liquid phase, in the gas phase, as well as exploring only spin states in the low magnetic field. So this appears to be quite promising. Also, pyrohydrogen is being used to enhance imaging experiments, in this case to obtain two-dimensional and three-dimensional maps of the product distribution in the model catalytic reactors. Now, supported metals work in HET-PHIP, but unfortunately not perfectly. So we are constantly trying to look for better heterogeneous catalysts to do that. And one of the trends is to explore the so-called single atom or single site heterogeneous catalysts. Like in this case, this is a palladium-indium system in which a palladium atom is surrounded by indium atoms which are inactive in the reaction. So basically isolating this single palladium active center here. And indeed, this catalyst provides substantial polarization levels at substantial reaction yields, enhancing the NMR signals substantially and also facilitating imaging of the gas phase. Now, I think that the advantages of heterogeneous catalysis for HET quite obvious, and in fact, they are pretty much the same advantages as in the industrial catalysis. And this is why there is a trend in modern catalysis to bridge this gap between homogeneous and heterogeneous catalysis. And basically, our work parallels very closely the developments in modern fundamental and practical catalysis. Now, very briefly, to show you the broad scope of the research that Kirill was involved in, we are also exploring the concept of sidearm hydrogenation introduced by Silvio Aime, hydrogenating precursors and then transferring polarization to C13 nuclei. We are trying to produce catalyst-free hyperpolarized fluids or solutions, in this case, hydrogenating the substrate vapor with the solid catalyst and then dissolving the product, hydrolyzing it, producing hyperpolarized ethanol in the solution, which is absolutely catalyst-free in this case. Of course, in the context of potential biomedical applications, aqueous hydrogenations are very important, and we've done that again together with our partners from US here. And also polarization to N15 nuclei allows one to extend relaxation times to many minutes. I should also mention the work that was done in the field of SAVOR, and one example, that demonstration of spontaneous SAVOR in high magnetic fields was already mentioned yesterday. Also, there was a demonstration again together with our US partners and colleagues from Novosibirsk that one can immobilize in the rhodium complex on a solid material and still obtain SAVOR effects using this system. So this is at least viable. Another approach is to do SAVOR in the traditional way using homogeneous solution, but then removing metal complexes using these thiol functionalized solid materials and producing clear catalyst-free solution of the polarized molecules. Also, there's been work done on the hyperpolarization of nitrogen-containing drugs. For instance, here the picture shows that hyperpolarization of pampridine allows one to perform imaging using N15 signal detection at natural abundance of N15 isotope. Now, coming back to that very first joint project, which I mentioned in the beginning, I'd like to draw your attention to this last item here, which was about ultra-low field magnetic resonance in metal containers for monitoring heterogeneous catalytic processes. And this has been achieved this year in a collaboration with the group of Dmitry Butker in Mainz. So here, these compounds were hydrogenated with pyrohydrogen in a metal tube, and the NMR spectra were detected with an atomic magnetometer at zero magnetic field, demonstrating that this approach is indeed promising for applying to heterogeneous systems and studying heterogeneous catalytic processes as well. Now, one last example of the experimental results which I'd like to mention is the work which was done by Vladimir Zhivanitka while he was still in Novosibirsk. So for many years now, we've been trying to think outside the box and actually trying to go beyond perohydrogen. This is an example of the hydrogenation of acetylene with perohydrogen in order to enrich spin isomers of ethylene. But ethylene is a symmetric molecule, so to demonstrate that the reaction with, for instance, this compound, sulfonyl chloride, is required to produce a non-symmetric product. And when this was done, then one can clearly observe these HET-PHIP signals proving that indeed the enrichment of spin isomers of ethylene is taking place in this process. But this is an indirect proof. So since then, we've been trying to do more direct experiments to confirm that this chemical synthesis of nuclear spin isomers works. And it is based on the optical detection of ethylene in the gas phase. And this fragment of the IR spectrum of ethylene, you can see several lines, and each belongs to a certain spin isomer of ethylene. So the idea is that when we do this reaction with perohydrogen, we should be able to observe the changes in the relative intensities of the signals. So we believe we have demonstrated that, but we are still trying to finalize these experiments to prove beyond doubt that this is indeed a possible way of enriching spin isomers of ethylene. Now, some statistics, bibliometrics. Kirill has co-authored about 100 peer-reviewed publications, including some well-known chemistry journals. He has made presentations at various national and international conferences, including this Euromar 2008 in St. Petersburg, where he received the Wiley Award for Young Scientists from Jeffrey Bodenhausen. He was, of course, a very important and irreplaceable member of the group. Here you can see him standing between Danilo Barsky and Vladimir Zhivanitka, who were still in Novosibirsk at that time. There is a later picture, you can see him here. And this is probably one of the latest photos where he's still with us. He was supervising many undergraduate and graduate students, and some of them will be presenting their results during this meeting. It was a privilege to know him and to work with him very closely. But somehow I always preferred that we would be sitting, not standing when talking to each other. I don't know why exactly. Now, in the very end of last year, Kirill defended his habilitation thesis, and this is a major milestone in someone's scientific career. So he was very eager and excited about starting a new chapter in his life, about starting new scientific projects, about addressing new scientific challenges, not knowing that it is going to be a very short and very dramatic chapter in his life and in our lives as well. I would like to thank our partners and collaborators in different parts, many parts of the world, especially Eduard Chekmenyov, our longtime partner and friend, and in particular for setting up this fundraiser to support Kirill's family, and you can find this information on the PERM website. And one last thing which I would like to say is that life is short, and sometimes it is actually a lot shorter than it may seem. And I think we all should remember that. And with this, thank you very much for your attention.
Igor, thank you very much for the exciting presentation. The floor is now open to questions. In case if you would like to answer a question, feel free to raise your hand or type the question privately to me and I will voice it for Igor. I'm going to start with the first question. Actually, with the first two questions, because it came as a series of questions. So the question goes as follows. How does one choose between platinum or palladium for the catalyst active site in the heterogeneous catalysis? Do they have notably different properties?
Well, they certainly do. There have advantages and disadvantages, but in terms of using this for PHIP, it is not a very simple matter. Some catalysts can be very selective for a certain reaction, like for instance, the one I've shown you with palladium-indium system is very selective in hydrogenation of a triple carbon-carbon bond to a double bond, but not double bond to a single bond. So this is not a simple matter, and we do not have any rules for selecting this. We are still searching and trying to gather information, trying to understand how this catalyst works. Because what I can tell you is that while we know that perohydrogen is a very useful reporter molecule for studying heterogeneous catalytic processes, we are still basically learning the language, trying to find out how this works. This is complicated by the fact that in fundamental catalysis and industrial catalysis, people are studying the main reaction mechanism, and they're still having troubles to find out what the mechanism is. In our case, we know that with metals, we're dealing with a minor reaction channel, so it makes it a lot more difficult to find out the mechanisms and to find out better catalysts.
Thank you. Here's the next question for you. In the case of filterable iridium catalyst for Sabre, is it possible or is it worthwhile to recover and reformulate the iridium catalyst itself?
Well, this is certainly one of the goals in industrial catalysis, but as far as PHIP and Sabre studies are concerned, I do not think so. I think it would be more useful to actually always start with the fresh system, get the maximum polarizations. But that's just my opinion. I do not have a certain answer for this. This still has to be researched.
Thank you. Here's one more question. The question goes as follows. Doesn't the more recent work from Bouchard's group, where they use capping groups on catalytic particles to give lower yields but higher polarization, support your hypothesis of the islands of localization for parahydrogen and substrate to give rise to heterogeneous PHIP effect?
Maybe it does, maybe it does not, because there are other possible explanations. For instance, suppose you have two different types of active centers. One is pairwise and another is non-pairwise. And what often happens in catalysis is that when they introduce a poison, the poison acts differently on different types of active centers. So you're maybe poisoning the non-pairwise site more significantly than the pairwise site is poisoned. And therefore, this explanation is not 100% proof. You know, there are other possibilities, and further work is needed to actually find out why metals actually work.
All right, here's some more questions. The next question is the following. The infrared measurements for the ethylene isomers are very interesting. Did you try cooling the ethylene to simplify the spectrum?
Well, actually, we do not need to simplify the spectrum because we see each individual spin isomer in this spectrum. What we do, we go to fairly low pressures so that we have sufficient resolution to see each one individually. I do not see any advantage in going to lower temperatures, but maybe there is one. I'm not sure.
Okay, and one more question, several more questions. The question goes as the following. Molybdenum sulfide catalyst can give rise to the PHIP signal. is the molybdenum sulfide MOS2 2D material?
Well, what we did work with, I think it's not a 2D. I think it's a 3D material. But nowadays, people, for instance, with carbides, they work a lot with planar 2D materials as well, and those also give some HET effects, not very large ones. But in my opinion, if we want to have the highest possible polarization levels, we should stick to platinum group metals because they're most active. And what we need, as for instance, James mentioned yesterday, is not just high polarization. We need a product of high polarization times high conversion. So in this sense, I think platinum group metals should work better, except we still need to find those which would give substantial enhancements as well.
All right, one more question. The question goes as this: I'd be interested to hear more about spectroscopic measurements of spin isomers in gases like propane. You said that the experiment did not show a clear result or something like that. Can you elaborate more on this, please?
I'm not sure what the question is about, but propane has no nuclear spin isomers. It is not a symmetric molecule, except for this CH3 roller, of course. That's a different story. But overall, propane is not a symmetric molecule, so it has no nuclear spin isomers, basically. So I'm not sure which exactly slide the question is about. With ethylene, maybe this was about ethylene, where we do see polarization. It is quite convincing to us that we do have enrichment here, but still we would like to have a more direct proof to see that we do indeed have different amounts of different spin isomers of ethylene directly using optical spectroscopy, not through this second hydrogenation step, second reaction step.
Thank you. One more question. With respect to the ultimate relaxation time of the long-lived singlet state in the gas phase, what do you believe will be can be the ultimate limit for the TLLS?
Well, it depends on the system, of course, because, for instance, perohydrogen lives for many days and months under appropriate conditions. With ethylene, there has been some work, optical studies done, and ethylene has 4 spin isomers, and some interconversions are indeed very, very slow because they are parity forbidden, and the lifetime of actually not just many seconds, but many minutes are possible. But the problem is that there is no reliable and efficient way of producing these spin isomers, and this is a problem, and this is why we are working on this system.
All right, thank you very much for questions and answers. Well, with this, I would like to thank Igor one more time for his very exciting presentation. Thank you very much, everyone, for your questions, and we would like to move on to the next session.